Alright, so now this is the final part of the chapter. I know it's been a long chapter, but um, we're going to be talking about numbering system applications. So we learned all about these fancy number systems and the ASCII table and all that stuff. But how do we apply it to real life? So this is just going to go over a set of examples as to how we can use these number systems and methods for real applications. So because digital systems have to work with ones and zeros, learning the different numbering systems can be important, and which system you use is, you pretty much have to go by context. I mean, how is the data developed? How is the data going to be used? So we're going to look at several different numbering system applications. The first being this 4 chemical storage tanks. So they're shown there. They're being monitored for temperature, T, and pressure, P. And you can see each tank's pressure and temperature sensors are leading into whatever monitoring system is tracking temperature and pressure. And if temperature or pressure goes outside of normal bounds, it is to trigger some sort of fault in the computer system. So if we think about how we want to organize these, because we have 4 tanks with two sensors each. So the total of 8 different possible inputs to this computer system. Well, what if we take the P and the T, sensors for each tank, and we just say, okay, 0 means that there's nothing wrong, temperature or pressure, whichever sensor it is fine. 1 means there's an error, like, pressure's too high or too low, temperature's too high or too low, some sort of error. Then we can compile a binary string. We can make these 8 separate sensors into basically a binary string. And we can use that binary string, sometimes it's called a bit field, because it's just a field of bits with each bit indicating the status of something. And in this case, it would indicate the status of the particular tank and the pressure or temperature of that tank. And so at the bottom there, you see the various sensor inputs, and we've organized them into the most significant bit being the pressure of tank D, and then from left to right, going from most significant to least significant bit, it's the temperature of tank D, the pressure of tank C, the temperature of tank C, and so on, up until the temperature of tank A. So they're asking if the computer reads a binary string of 0010 1000, that full string. Well, they're asking what problems exist. Well, we know that any 1 is an indication of an error. So the problems are at the locations where the bit is 1. And it happens in 2 spots in this example. It happens on bits, if we number them with the most significant bit here being bit 7, we'll say, and the least significant bit here, this last 0, being bit 0, then we can say that there's an error on bit 765. Bit 5 has an error. And then also bit 3 has an error. Which, if we look down here into how we organized, probably be easier to just write these out. So we have a, let's use red. We have a 0. Actually, I'll write it up here. 0. It's a horrible 0. 0 here. There's a 1 here, a 0 here, 1, 0, 0, 0. So there's our number matched up to the various pressure and temperature. Basically, each of these bits is mapped to a particular tank and a particular sensor on that tank. We know that ones mean an error, so we're really just concerned about this here and this here. So based on this string of bits, if the computer is reading out this series of 8 bits, we know that the pressure sensor for C, the pressure in tank C has an error, and the pressure in tank B has an error. Or it indicates that the pressure in tanks C and B are too high. So then they're saying, using the same table, if the computer reads a hex value of 55 hex, the H just means it's a hex number, and just FYI, we can also you'll also see oftentimes numbers written in hex as 0x whatever, the 0x indicating that it's a hex value. But here they're using the H to indicate that. So anyway, we're saying the computer reads a hex value of 55. Well, when we can convert that into a binary number and then do the same thing we did in the last example. So first of all, we're remember that all we have to do for going from hex to binary is just take each individual hex character and convert it to 4 bits. So for the first digit of 5, it would be a 0, 1, 0, 1. And the second digit is also a 5, so we would see 0, 1, 0, 1. And so it looks like, if all the ones are errors, it looks like every single tank has a temperature problem. And that's exactly what it indicates. All the tank temperatures are too high. So then, kind of in reverse from before, they're giving you the condition. They're saying the temperature and pressure in tanks B and D are too high. And they want to know what hex value would be read by the computer. Well, let's start with just getting the binary value first, and then we can convert it into hex. So the binary would be, they're saying tanks B and D are too high in temperature and pressure. So where is tank B? That would be here. So we're saying that the temperature and pressure are too high in tank B, so both of these would be a 1. And the temperature and pressure in tank D over here are at fault, so those would be 1s as well. And then the rest of them don't have problems, so we'll just put 0s there. So our number is 11001100. So now all we have to do is convert this into hex. So now we take groups of 4. So, these 4 bits, one group, these 4 bits, another group. And because they're identical groups, both of them are 1100, we can just, we just convert the first one and just duplicate it. So, 1100 is the number for 8 plus 4, which is 12, which 12 in hex is represented by the letter C. So it would be C and then C again. CC would be the hex value read by the computer. So then another example. So enough about the tanks and stuff. Let's move on to a CD player, we'll say. It's converting 12-bit signals from a CD into equivalent analog values. It's asking what the largest and smallest hex values that can be used in the system. Well, the largest, so they're saying it's 12 bits, so we know it would be 3 hex values because each hex value is 4 bits, so we just divide 12 by 4, you get 3 different hex digits. And we know that the highest digit in hex is F and the lowest is 0, so naturally the lowest number in hex would be 000, for 3 digits at least, 000, and the highest number would be FFF. So when they ask how many different analog values can be represented, we just take the highest number, they take the highest number here and convert that into decimal. FFF converted into decimal, if we were to use our methods that we that we used previously, we would find out that it's 4095 is the highest value, but it also includes 0. So there are 4096 unique values. So then, let's say digital thermometers. Typically, they'll use BCD to drive their displays. So they'll have a binary coded decimal binary string, zeros and ones, one set of 4 representing each digit on the display. Now remember that BCD uses groups of 4 bits for each number, so when they ask how many BCD bits are required to drive a 3-digit display, all we do is multiply 3 by 4, and we find out that it's 12 bits that are required, 4 for each digit. And then they ask what 12 bits represent 147 degrees Fahrenheit. Well, in BCD, we just take each number. We would just break off 1, figure out what 1 is in binary, figure out what 4 is in binary, figure out what 7 is in binary, and determine each digit separately, what 4 bits represent that digit, and then we just put them all together. So if you do that, and I'll go ahead and erase that ink, we would translate 1 into 0001, 4 would be 0100, and 7 would be 0111. So another thing is that a lot of PC systems or PC compatible systems use addresses, and in this case they're saying 20 bits for an address code to identify each memory location. There can be millions of memory locations. I mean, you know, you've heard the terms megabytes, gigabytes. That's how many different memory locations that you can have. So you can figure out how many hex characters are required to identify the address of each memory location. They give you that it's 20 bits of an address code. We know that hex characters can represent 4 bits each. So 20 divided by 4 would be 5. So we need 5 characters to represent 20 bits. And then here's an ASCII application here. Let's say we have a part number of some part. That's 651-M. Well, we can represent that. Remember that ASCII is a way for us to represent letters, numbers, symbols, all that stuff, represent text that we see, using a coding system where each binary string of 8 bits, or technically 7, but up to 8 bits, can represent a single character. So if we were to look up an ASCII table, you can, Google an ASCII table. We could go back, to the other ASCII table that was earlier in the slides. But basically, you would use an ASCII table as reference, and when they ask what the binary contents of the memory locations would be, all we have to do is look up each of these characters individually on the ASCII table, figure out what value represents that character, and just convert it to binary, and that would be the contents. So if we were to look up on the ASCII table the number 6, we would find that the ASCII code for 6 would be, 36 hex, which then when we convert it to binary would look like this. And then same thing with 5. We would find out that we would find its hex value is 35, and converting 35 hex into decimal or into binary would yield this result here, and so on for each of the characters. And even the dash has its own unique ID code. So that's how you would figure that out. so then once we establish each individual character's value, now we can put all the bits together in sets of 8, not 7. So we just add leading zeros to each of these values, and it's all just a consecutive string of bits to represent that 651-M part number. So that's how we can use ASCII. So in this example, they're talking about a programmer who has a debugging utility. He's trying to find an error in a BASIC program, and BASIC is a pretty old programming language, but that's what he's using. So the utility he's using shows an ASCII code as that hex number that they show there. So it's just a big jumble of hex values. So if we assume that the leftmost bit of each of the ASCII string is padded with a 0, we can use our ASCII table to then, well, first of all, we would want to separate these, right? We would want to separate them into groups of 2, because it's 2 hex characters per ASCII character. So we would split there, 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 and there. So 4-7 is one character, 4F is another, 5-4 is another, and so on. So we would just look up on our table the values here, these hex values. If we're using that other table from the ASCII table slide that was previously shown, we would we might have to convert these into binary because that table used or displayed the values as binary. But regardless, either way, we're using each of these groups of 2 hex characters individually to represent, or to look up what character that value represents. And when we do that, we find that the letters spell out this string here with the 2-0 value, hex value, representing the space in between this 0 and this 9. So this space is actually a character. It is the 2-0 character there. So after we translate with our handy-dandy ASCII table, we find out that this is the string that the utility is showing as being the error. And the error is, well, it looks like the programmer meant to type go2, but he typed a 0 instead of an O. So that's what threw the error. All right, so that's it for chapter 1. I know it was a doozy. So we covered numerical quantities and how, in the real world, most things are analog, but all of our computers are digital, so we need to often convert from analog to digital or digital to analog in order for us to actually use the data. So we also covered the binary system, base 2. It's used in digital systems because the zeros and the ones are easily represented by on or off transistors. So it's easy when you just have an off state and an on state, and that's it. And for example, the TTL system, which I believe stands for transistor to transistor logic, it's just a standard that says 5 volts is a 1, 0 volts is a 0, and that's it. And those are the voltage levels for the on and off signals. So any of these number systems that we covered can be converted to decimal by multiplying each digit by its weight factor. It's that multiply by weight method that we went over. The weighting factor for the least significant digit in any number system is always 1, because it's always, the base number to the 0 power, which anything to the 0 power is 1. So that's just a little, tip that the first column is always going to represent a 1, and then subsequent columns are going to represent, whatever the base is to whatever power. Binary can be converted to octal very easily by forming groups of 3 bits, and then you can convert binary to hex by forming groups of 4 bits. Makes it a lot easier. The successive division procedure, we went over that. That's used to convert from decimal to another system, whether it's binary, octal, hex. We also touched on the BCD system, binary coded decimal, that it uses 4 bits, exactly 4 bits. And the usefulness of that system is that it can drive decimal displays like those on a calculator, or a digital thermometer, I think was the other example that they showed. And then we also covered ASCII and how we can translate characters into, or rather we assign characters number values, codes, that allow us to identify unique characters, individual characters. And this system is used by computers to represent letters, numbers, symbols in digital form. Sometimes representing non-printable characters that you don't even see but are still there technically, and they do have values in the ASCII table. So that concludes Chapter 1.